This conference will now be recorded.
Good evening, everyone. Last day we have started ozone, which is allotropic form of oxygen. Today we will see what are the chemical properties of ozone, and after that what are its application. And after these allotropic forms of oxygen, that is ozone, there will be discussion related to different allotropic forms of sulfur. And also one of the important compound of sulfur is sulfur dioxide. Its preparation, properties, applications, all these will be discussed. Chemical properties of ozone, how it acts as oxidizing agent, that we will see. Due to the ease with which it liberates atoms of nascent oxygen. We have already seen that O3 is very unstable molecule. It has a tendency to convert to O2 gas, that is the diatomic form, and also one oxygen atom, which is also known as nascent oxygen. And this nascent oxygen is actually responsible for its oxidizing capacity. Okay, and this conversion is it occurs very easily, so that is why it will be very powerful oxidizing agent. Here the first example we have K2MnO4. It is not potassium permanganate, it is potassium manganate. Okay, where oxidation state of manganese is +6. It is reacting with O3 and it is converted to now permanganate, that is KMnO4. So from +6 now the oxidation state is +7. That means oxidation is taking place, and O3 itself is converted to O2. In each of these reaction, one thing you will see which is common, that in each equations O3 is converted to O2. Next equation Ki, that means -1 is the oxidation state of iodine, but after oxidation it is converted to 0 oxidation state. So this is also example of oxidation reaction. Third one is, now if we consider PbS, then oxidation state is +2. After reaction we are getting Pb sulfate, lead sulfate. This is also having oxidation state +2. So with respect to lead, it is not oxidation. But now if you look at sulfur, it is having oxidation state -2, and in sulfate ion, that is SO4 2-, sulfur having oxidation state +6. So that is why it is oxidation with respect to sulfur from -2 to +6. Number 4, nitric oxide, it is converted to nitrogen dioxide. That means from +2, now it is +4. So this is also oxidation. Some more examples. Directly if we take sulfur, then it is converted to H2SO4. So from 0 oxidation state, now it is +6. Then NaNO2, that is sodium nitrite, which is containing NO2- ion. Now Na2- ion, here oxidation state of nitrogen, it is +3, because overall charge is -1. Each oxygen atom -2, so -2 into 2, -4 is the total negative charge. So excess 1 negative charge is present. So that is why it is NO2-. So this is nitrite, but now it is converted to nitrate, NO3-. Now oxidation state is changed to +5. So from +3 to +5. So this is also oxidation. And the last reaction, where mercury from metallic state, now it is converted to Hg2O. And in this reaction, mercury losses its fluidity, because when it is under normal condition, we know it is fluid in nature. Okay, but when it is converted to Hg2O, that is, there is visible appearance change. So this type of phenomena, that is known as tailing of mercury. So question may be asked that tailing of mercury, it occurs because of which gas? Then the answer is, it is ozone. It can also act as reducing agent, but mostly we'll see the reactions that are mainly based on oxidizing power. That is, ozone is showing oxidizing power, but some reactions are also there where it is acting as reducing agent. Here we have some examples. H2O2. So this is hydrogen peroxide where oxygen is having -1 oxidation state, and now it is in presence of O3 and it is converted to H2O. That means oxidation state is -2. So from -1 to -2, that means it has accepted electron. So that is why it is reduction. Then we have barium peroxide. Again, it is peroxide. That means -1 oxidation state, and after a reaction, it is now -2. Then PbO2. Here also same thing. Now it is converted to -2. And Ag2O. Now Ag2O, it is with respect to silver reduction, because when it is silver oxide, it has oxidation state +1. But after reaction, now it is metallic silver, that is oxidation state 0. Okay. Next example is for ozonolysis. Now this reaction is mainly from organic chemistry, which is very famous reaction, and this reaction is used for alkene to cleave this CC bond, and O3 is used for this reaction. And this reaction is very one of the important application of ozone gas. Now what happens here in presence of O3? First, there is formation of this type of cyclic 5-membered ring. Okay, 1 oxygen, 2 carbon, then these 2 oxygen. This is the intermediate, but this is not the final product. Next, what happens? There will be cleavage of oxygen carbon bond, and from this part and this part we will get, that is in the next step, which is known as basically decomposition. In this step we will get 2 aldehydes. One is RCHO, another one is R prime CHO. So from both sides we are getting 2 different aldehydes. So that is why it is mixture of aldehydes, because R group is different. If it is same R group, then it will be same aldehyde. Okay. And H2O2, that means H2O is converted to H2O. So in this way we can cleave the CC double bond by ozonolysis reaction, that is using O3. Here we have one method which is used for estimation of ozone. It is actually not directly chemical properties of ozone, but here we will see this because you may get question based on this. When ozone reacts with an excess of potassium iodide, that means you have taken excess Ki, and there is it is buffered with a borate buffer which is having pH 9.2. Now when we use buffer, there are different types of buffer solution, and we use buffer when we want the pH to remain fixed. Okay, so buffer actually helps us to maintain the pH. So here we need the pH which is around 9, and that is why borate buffer is used. Now Ki in presence of O3, what happens? We have already seen that Ki and O3, you can consider this reaction in the left hand side box. Here Ki is oxidized to iodine, so iodine will be liberated. Now this liberated iodine, it can be titrated against a standard solution of sodium thiosulfate, that is Na2H2O3. Now sodium thiosulfate is reducing agent, so what it will do, it will reduce iodine again to I. So this is a standard solution of sodium thiosulfate, that means concentration of Na2H2O3, it is already known. Okay, now why it is quantitative method of estimation of O3? Suppose you do not know what is the amount of ozone that is present, and what you are doing, you are reacting O3 with Ki and it is present in excess. Now what will happen? Here O3 will be converted to O2 and you will get iodine. Now this iodine in presence of the reducing agent, that is Na2H2O3, again it will be converted to NaI. Now the reducing agent that we are using here, which is Na2H2O3, its concentration is known. So if you know the concentration of Na2H2O3 And from the balanced equation, you will be able to understand how many moles of Na2H2O3 is reacting with iodine. So in this way, you will be able to know what is the number of moles of iodine liberated. Now, if you know the number of moles of iodine liberated, you can also find the number of moles of O3 from the balanced equation. So in this way, we can estimate the quantity of O3 if it is unknown. Okay. So for estimation of O3, we are using potassium iodide solution, and the liberated iodine, we are titrated it with Na2H2O3, which is a reducing agent. So in this slide, is there any doubt? Should I repeat it once more? Application of this gas: water treatment plant without filtration system, that is for purification. Then ozonolysis, it is used as reagent, and ozonolysis reaction, it is also used for detection of position of double bond, because when the CC double bond is broken, you are getting two different carbonyl compound. Okay, so if there is any molecule, suppose very large molecule, and you know that there is CC double bond, but you do not know what is the actual position of the double bond, that is the location of the double bond. But after cleavage, if you can identify the carbonyl compounds that are produced after ozonolysis reaction, then you will be able to understand what is the position of the double bond, that is location. It can be used to detoxify cyanide waste. In medicine, ozone therapy is used to disinfect, and because it has oxidizing capacity, to treat disease by limiting the effects of bacteria, virus, fungi, yeast, and protozoa. So it can destroy all this. Okay, so that is why it has some therapeutical use. Now we will see ozone depletion, which is very important phenomena. There is different layers in the atmosphere. This is troposphere, which is 0 to 12 kilometer from the Earth's surface. The next one is stratosphere. Now in the stratosphere zone, you can see this is the ozone layer, which is around 20 to 30 kilometer from the surface of Earth. Now, the sunlight that is coming towards us, there are presence of different wavelength, short wavelength, long wavelength. Now the short wavelengths, that is the UV, visible light, and then IR, what happens? All these different wavelengths are present, but the UV ray, that is actually harmful for us. Much of the harmful UV radiation absorbed by ozone layer. But because of the presence of this ozone layer, that is this blue band that you are seeing, circular blue band, that can absorb the UV radiation. So see, only the visible light is coming towards us, but not the UV radiation, because it is absorbed by O3. So in this way, this natural presence of the layer of ozone, it is actually helping us that is protecting us from the harmful effect of the UV ray. But somehow, if this ozone layer is destroyed, then what will happen? The UV ray, it will directly come towards us, okay? And that is obviously not desired. So that is why it is called ozone depletion. Now, what is the actual, by this term, what you are trying to mean? Ozone layer depletion, it is the gradual thinning of this Earth ozone layer. That is the natural presence of ozone layer, which is present in the upper atmosphere 20 to 30 kilometers from us. Now, the depletion of this ozone layer, it will have some harmful effect on human health, animals, environment, marine life. Now, what are the causes behind it? Mainly the cause for this ozone depletion, or sometimes it is also called ozone hole. That is, if there is a hole created here, then also the UV can come towards us through this hole. Now, this is because of some manufactured chemicals, specially manufactured halocarbon refrigerant. Halocarbon means halogen carbon, this will be present. For example, CFCs, that is chlorofluorocarbon. That means chlorine, fluorine, carbon. These three elements are present. Then HCFC, that is hydrogen, is also present, halogens. So all these chemicals are actually responsible for ozone depletion. And there is also presence of propellant, that is different oxides of nitrogen, that is also destroying the ozone hole. For example, nitric oxide plus ozone. Now ozone is converted to O2. That means ozone layer is destroyed. Okay, so this is ozone depletion, which is not desired. Any doubt? Now, related to ozone, we will discuss two problems. Out of the following, which does not liberate nitrogen gas on heating? Now, it is not purely related to ozone, because you will see that here some group 15 element, that is nitrogen, that is also present. So you can consider it as if it is based on P block elements problem. There are 4 reactions given: NaNO2 reacting with NH4Cl, then barium azide, it is actually simply heated there because there is no other reaction partner. Then O3 reacting with NO and ammonium dichromate, K2, just like K2Cr2O7, but now it is NH4 plus if it is heated. So the question is, in which case you will not get any nitrogen gas. Now see, even if you do not know all the products of all these 4 reactions, then also you can answer this question. Remember this equation, we have just seen it in the previous slide, how NO is reacting with O3. See, in the bottom box, there is a reaction mentioned, NO plus O3 is converted to NO2 and O2. So O3 is actually oxidizing agent. Okay, that means here oxidation state of nitrogen is +2. Now if O3 is oxidizing, that is fine. So obviously you cannot get here nitrogen because nitrogen is having oxidation state 0. Now from +2 you are getting 0 oxidation state. That is not possible by O3. So in this case you cannot get nitrogen. So this much information is enough to answer this question. Even you do not know what are the products in these cases, because it is single choice answer. So there will be only one option in which there will be no liberation of nitrogen. So that is why this is the correct option, that is option 3. But we will also see that what are the products in other reactions. Sodium nitrite, NH4Cl, here obviously if nitrogen is not liberated in the third option, in the rest of the 3 options 1, 2, 4, there will be liberation of nitrogen, that is confirmed. So when nitrogen is liberated, barium azide, when we are heating it, azide means N3 minus ion is present because barium is having oxidation state 2 plus, so 2N3 ion is there, N3 minus ion is there. Here we are getting nitrogen, but here no nitrogen. In the last one also, when it is heated, nitrogen gas is liberated. Okay, so option 3 is the correct option. Assertion reason type of question. It is necessary to use silent electrical discharge in the preparation of ozone to prevent its decomposition. This is the statement given in assertion. Now remember, in last class we have seen how we can make ozone by silent electrical discharge tube. Okay, and there we have mentioned that it must be silent. Now what is the reason behind it? Here in the reason, the statement that is given, it is saying that formation of ozone from oxygen, it is exothermic process. That means from O2 you are getting O3. This process is exothermic. That means some energy will also be released. But is it so? That we have to find out. Now, if we look at the options, first we have to see that whether both the statements are correct or not. Then the next question arises, that is, suppose if assertion is correct, reason is correct, both are correct. Then the next question arises whether reason is the correct explanation of the assertion statement or not. But first we have to see whether it is correct or not. The first statement, that is, it is necessary to use silent electrical discharge, this is actually correct. That we have already seen during the preparation. And consider the statement which is given in reason. Just forget about the statement given in assertion. Individually, that is independently, first we have to see whether this statement is correct or not. So it is saying formation of ozone starting from oxygen, it is exothermic. But it is not exothermic, it is actually endothermic. So plus daily, it is not correct. Here actually energy is absorbed. Energy is not liberated. So it is not exothermic. Remember this type of graph that we have seen. So product energy is higher than starting material energy. That means it is endothermic. Here del H value is positive. Okay. So the statement which is given in reason, that is not correct. So the question that whether it is correct explanation or not, that does not arise. That is whether R is correct explanation of A or not the correct explanation of A, that question arises only when R is correct. But in our case, R is not correct. Okay. Now what is the actual reason? Why we use silent electrical discharge? Because to avoid decomposition. Because this process is endothermic. Now endothermic process means you are providing some energy, it is absorbing energy. But if it is not silent, there will be some wastage of energy by the production of sound, which is not desired. We will try to save energy as much as possible, because in this reaction, if somehow energy is wasted, already the yield is very low. You have seen it in the last class. It is very low yield, but in spite of that, if you are wasting the energy, then further yield will be lowered. So that is why it is critically maintained. That is some steps we have to check whether it is present or not while making O3 from O2. And this is the important condition, that it must be silent to prevent its decomposition. That means the O3 that you are getting, obviously you will try to maintain it, but if it is again decomposed to O2, that is obviously not desired. We will try to stop this. So that is why, to prevent its decomposition, since the formation of ozone from oxygen is endothermic process. So that is the actual reason. So here the statement is not correct in the reason. So this will be the correct option. A is correct, but R is not correct. Any doubt? Now we'll see allotropic forms of sulfur. So allotropes are different physical form of the same element, and because of this difference, there is also effect directly on their chemical properties and physical properties. So here we have a flow chart. Allotropes of sulfur. The first, that is, we have divided it in two categories. One is crystalline form, another one is amorphous form, that is, which is not crystalline. Under crystalline, you have two types, rhombic and monoclinic. These terms, we know there are total 7 crystal systems. There we have already seen this type of terms. Okay. And under amorphous forms, there are mainly three types. There are some other insignificant forms are present, but these 5 forms mostly very common. Okay. So the first type that we'll discuss is rhombic sulfur. It is also known as alpha sulfur. You should also know what is another name it is that is used for rhombic sulfur, because if in question it is given by using the term alpha sulfur, you will not be able to recognize. So that is why both the names we should remember. It is the only thermodynamically stable allotropic form. So from thermodynamic point of view, it is most stable. Okay, when you are considering ordinary temperature and pressure under normal condition, this is the most stable form. Melting point 114 degrees centigrade, and the crystals composed of S8 molecules have a characteristic yellow color. Water solubility, it is insoluble in water, but if you take some organic solvents like benzene, alcohol, ether, solubility better than water. But if you take carbon disulfide, This is also organic solvent. Now the solubility is very good. It is obtained by, that is how you can make it, by slowly evaporating a solution of roll sulfur. So see, this is the picture of rhombic sulfur. Okay, that is the crystalline form that you are seeing. And how we are making it? By slowly evaporating a solution of roll sulfur in carbon disulfide. Now roll sulfur, there is a specific term we are using. This is actually the roll sulfur. Roll sulfur is the sulfur in the form of rods. You can see it is having the form of rods or sticks. That is, it is just like chalk. Okay, by casting molten sulfur. So this roll sulfur, what you are doing, you are slowly evaporating a solution of this roll sulfur. This is roll sulfur. And you are doing it in carbon disulfide because solubility is very good. Now, what next step? Solution of sulfur in carbon disulfide. Now you are filtering it through filter paper. So the insoluble part that will be remaining here, and this is the solution of sulfur in CH2. So gradually when this solution is evaporated, there will be appearance of SH crystals, that is the octahedral crystal. Okay. So in this way we can make it. And this is a picture of alpha sulfur. Fine. This is the first form. The next form is beta sulfur or monoclinic sulfur. This form of sulfur, how we can make it? By melting rhombic sulfur. That means the first sulfur that we have seen, now we will take the help of that sulfur because that is very stable under normal condition to make beta sulfur. So beta sulfur we are making starting from alpha sulfur. And it looks like this, that is beta sulfur. It has needle-like shape. It exists as long needle-like prism, also called prismatic sulfur. So it is called monoclinic sulfur, beta sulfur, or prismatic sulfur. Now, how we are making it? By melting rhombic sulfur in a dish and cooling. So first there is molten sulfur present. Now when it is already heated condition, it will be in liquid form. Gradually when it is cooled down, then there will be appearance of crust like this. That is on the surface, there will be formation of crust. Now next, if we break this crust pierced by some hot nail. So suppose we have made some holes in the crust. Now the needle shaped prismatic sulfurs we can get. So after removing this crust, you can get the needle type of shaped monoclinic sulfur. Now there is a temperature which is 96 degrees centigrade temperature. Below this temperature, it is unstable. But if it is at 96 or greater than 96, then only it is stable. But if it is below 96 degrees centigrade, it will revert to rhombic form. Because we have already said that under normal condition, rhombic sulfur is the most stable sulfur. So that is why, remember, this is the transition temperature, because at this temperature, why it is important? Because below this temperature you have alpha form, that is rhombic form, but above this temperature you will have beta form, that is monoclinic form. So that is why it is called transition temperature. So these two forms are under crystalline category. Now we will see here some more information regarding transition temperature, because this is a general term, it is not just for sulfur. You can see the use of this term in other places. So what is in general the definition of transition temperature? The temperature at which one allotrope of an element changes to another allotrope of the same element. That temperature is called transition temperature. Now these allotropes that can change their configuration from one form to another by some changes in temperature, they are known as enantiotropic allotropes. So this is the definition of enantiotropic allotropes. Remember, though the name is enantiotropic, it has nothing to do with enantium. Okay, that is completely different thing. So here these alpha and beta sulfur, you can call them enantiotropic allotropes because they are related to each other by this transition temperature. Okay, so that is the reason these alpha and beta sulfur, they are also enantiotropic allotropes. Now some common features for both rhombic and monoclinic, both of them having acid molecules. These acid molecules are packed to give different crystal structures. That is, acid is common, but how the packing is occurring, depending on that, you can have either alpha or beta. Now see, you can see these crown shaped figures. So when it is rhombic sulfur, all the orientations of the crown, it is towards the same side. See, orientation is same. But if you consider the second one, that is the beta sulfur, now this crown is inverted, then again this crown normal position. So now obviously the arrangement is different, but if you focus on the individual unit, it is actually crown shape and S8 for both. Why it is S8? See, total 8 sulfur atoms are there. Okay, so depending on the arrangement, we will have either beta sulfur or alpha sulfur. So is there any doubt in these two crystalline forms of sulfur? Next we'll move to allotropic forms of sulfur, but now these will be amorphous in nature. Under amorphous there are 3 more types: plastic sulfur or gamma sulfur. How we will make it? When we are heating sulfur near the boiling point, that means now it will be converted to liquid. It will be converted to vapor. Okay, but if all of a sudden we are cooling it, this is important. All of a sudden, you are not cooling it gradually, you are simply cooling it suddenly. How? By pouring it in cold water, then a thick mass is shaped, that is formed. Now this sudden cooling, what it does not give the chance to form the crystal. So that is why it is not having amorphous crystalline structure. Now we will have amorphous structure. So you are doing you are cooling it very quick. So there is no enough time for the atoms to arrange themselves in the crystalline ordered arrangement. Okay. So that is the reason now it is not crystal. This sort of sulfur, it is dark brown, sticky type of nature. That is polymeric type of structure. Insoluble in CH2. So see, as it is having polymer type of structure, to break this, it is really difficult. So that is why its solubility is also now that is not present in CH2. In case of crystalline sulfur, we have seen that solubility is good in CH2, but now it is not the case. On standing, it gradually changes to the rhombic structure. Remember, rhombic form, that is thermodynamically most stable form. So if you keep it gradually, obviously there will be conversion towards the most stable form. Okay. This is the first amorphous form, plastic sulfur or gamma sulfur. So you can see here the polymeric type of structure. This is n number of this S8 crown. This is crown, right? But now the arrangement will be such that, see, n number of this unit. That means it is polymeric in nature. Okay. Second amorphous form, colloidal sulfur or delta sulfur. Now colloidal form of sulfur, you can see this is the picture, may be obtained by passing H2S through HNO3. This is one method. Another method is by treating Na2H2O3 solution with dilute HCl. So here from H2S you are getting sulfur, that means from -2 state you are using oxidizing agent. So from -2 state now it will be in the elemental state, that is zero oxidation state. Similarly, by treating Na2H2O3 solution with dilute HCl also, this is another method. Then the third method, it may also be obtained by treating H2S with sulfur dioxide. Now the third method, you can see the equation here, SO2 plus 2H2S, oxidation, we are getting 3S. Now see, two different compounds of sulfur we have taken. If you consider SO2, here oxidation state of sulfur is +4, and if you consider H2S, here oxidation state is -2, and sulfur is 0. So with respect to S, this is actually gain of electron, so this is reduction, but in terms of H2S, it is actually oxidation. So here the oxidation that is written, that is basically with respect to H2S. Okay, so these are the different methods by which you can make it. And here if we see the solubility, it is soluble in CS2. Okay, now the third form we have to see, that is the last amorphous form of sulfur. Okay, this method is also given here. This one, Na2H2O3 with HCl. So see here, Na2H2O3, that is thiosulfate ion, you are getting two different sulfur compounds. One is elemental sulfur, which will be precipitated, and sulfur dioxide also. But this method is better, that is the SO2 H2S, you are getting sulfur and H2. The third amorphous form is known as milk of sulfur. How we can make it? When flowers of sulfur. Now we are using a new term here, which is flowers of sulfur. Actually, it is nothing but fine bright yellow sulfur powder. It is called in this way. Boiled with milk of lime, that means calcium hydroxide. A mixture of calcium pentasulfide is produced. That means this one, CaS5 is produced. And also calcium thiosulfate is produced, CaS2O3. H2O3 2 minus, and calcium having 2 plus charge, it is balanced. See, the formula for sodium is Na2H2O3 because sodium having oxidation state +1, but for calcium the formula is different, CaS2O3. Now this mixture, that is this mixture being treated with HCl, it gives a white amorphous precipitate. Now that is known as milk of sulfur. It is soluble in CH2. So we have seen that three amorphous forms. The first form, that is caustic sulfur, that is not soluble in CH2. It has some polymeric type of structure, but the next two forms, that is milk of sulfur and the other one, that is colloidal sulfur, these two are soluble in CH2. When heated, it is changed to yellow variety of sulfur. Now we will see some more forms. So you can say that these are other forms, but they are not so significant like these 5 forms. So that is why all these forms we are mentioning it just in simple one expansion. Okay. Several other modifications of sulfur containing 6 up to 20 sulfur atoms per ring. So see, huge variety possible. We will just see 2 or 1 example. In cyclo-S6, that is the simplest one, the ring adopts chair form. So it's like a cyclohexane chair form. Okay. At elevated temperature, around 1000 Kelvin, that means in terms of degree centigrade 700 something, S2 is the dominant form. Now you can find some similarity with O2 because in group 16, the first element oxygen, then sulfur, then selenium. So oxygen mainly remains as O2, that is the diatomic form, but sulfur doesn't remain as H2. But under this special condition, when the temperature is very, very high, now you can get this diatomic sulfur, which is just like oxygen. And during the discussion of oxygen, we have already seen in the molecular orbital diagram that oxygen is actually paramagnetic because of the presence of 2 unpaired electrons in that we have seen in molecular orbital diagram. Now, as sulfur is also existing just like oxygen, that is diatomic form, so this will also be paramagnetic like oxygen. Okay, so there will be some similar type of behavior. So it can be as that when sulfur can be paramagnetic, so the answer will be that at elevated temperature, when it remains in the diatomic form just like oxygen, then it will be paramagnetic. So this is a cyclo S6 form. You can find similarity with cyclohexane chair form. Okay, and the angle is 102, almost 100 degree, and this is diatomic sulfur, that is S2. You can find similarity with oxygen. In oxygen also we know 2 lone pairs are there. Here also you can see 2 lone pairs. So any doubt here? So from normal picture you will not be able to understand why it is paramagnetic. It seems as if all the electrons are that is even number, but in molecular orbital diagram we have seen that because of presence of 2 unpaired electron, it is paramagnetic. Should I repeat any part in allotropic forms of sulfur? Next important compound of not important compound of sulfur. Here we will see one extraction method of sulfur, and this process is known as Frasch process. Okay, so what we do in this process, sulfur is melted underground with the help of superheated stream. So this is underground, this is sand and clay, and here you have molten sulfur. But how you are getting it? First there is solid sulfur deposit, but you are passing hot compressed air, that means very high temperature. So this hot compressed air, when it is coming in contact with this sulfur deposit, this sulfur will be now converted to molten sulfur. Okay, now this molten sulfur, what the next process, pumping is done by passing hot compressed air. Now we are using hot compressed air for pumping process, and this will produce foam of molten sulfur which rises upward and is collected in wooden tubs. Now the reaction is like this. It is collected here, molten sulfur and water mixture. Now this is a ground level. Okay, this is underground, this is underground, this is ground level. This low density of sulfur allows the compressed air to push it to the surface, because now it has some foam type of nature, so it is very low density. And as it is low density, so that is why this anti-gravity movement is possible. Otherwise, if it is very heavy, this will be difficult. Okay, now the sulfur can be cooled down and solidified, and it will be obviously rhombic crystal, because that is the most thermodynamically stable form. From this process, why this process is so much important? This is actually extraction process of sulfur. It is important because from this process, the quality of sulfur that we are getting, that is very high quality. So that is why this process is important. Okay, so remember the term. Actually here just remembering the term is mostly important, because the question that we will get, that will be completely memory based, that in Frasch process, which suppose it is asking which element is extracted. Okay, and another very unusual thing is that the extraction that is in metallurgy chapter, the processes that we have seen, this type of process is it is not very common. So this is a special type of process for sulfur. Okay, that is unique method that we are seeing here. Now we will move to sulfur dioxide, that is SO2. Important compound of sulfur, that is oxide of sulfur basically. There are another oxide also, SO3, but this is sulfur dioxide. Look at this structure. Sulfur, it is using 2 electron for bond formation with this right hand side oxygen. Then 2 electrons as lone pair, that means they are non-bonding. Now we know that group 16 element, so its valence electron number is 6. Okay, so rest of the 2 electron is used for this coordinate bond formation. So this bond is actually coordinate bond. That means both the electrons in this bond, that is given by sulfur. So that is why sometimes this type of arrow is also used. And as oxygen is gaining electrons, so that is why negative sign, and sulfur is giving electron, that is why positive sign. This gas is found in volcanic eruption. Large amount of this gas is released into the atmosphere from power plant also, when coal and oil and that is used using coal and oil and copper melting plants. These are the that is naturally how sulfur dioxide is present in the atmosphere. How we can make it? Preparation method. If you are making it in large scale, then you have to burn sulfur in air. That means you are taking oxygen from air, and in this case 6 to 8% of sulfur is also oxidized to SO3, that is another oxide. So this is the undesired reaction, but a very small percentage is converted to SO3. Mostly it is converted to SO2, which is the desired reaction. Other methods, when sulfide ores, that is PBS, galena, then zinc blende, ZNS are roasted in air. Roasting process, remember in metallurgy we have seen it. In roasting process, oxidation takes place. That is, sulfide is converted to the oxide. Large amount of SO2 required for manufacturing of sulfuric acid and other industrial purpose is prepared by this method. Because SO2 has some other application. From SO2, we make sulfuric acid, which is another important compound of sulfur, and it has very huge application. So that is why SO2 we have to produce in large scale. So in this process, the SO2 that we are getting, so it is possible for us to get large amount of SO2, because SO2 is again required for preparation of sulfuric acid and also some other industrial application. Okay, so we have two reactions here, ZNS and FeH2. Both are sulfide, and in presence of oxygen it is converted to oxide. Okay, Fe2O3 and ZN. And this is actually the desired part here. But if it is laboratory method, small scale, then how you can make it? SO2 is prepared by reaction of metal or metal sulfide. Sulfite, that means SO3 2 minus. Sulfite is SO3 2 minus. So you can take directly metal, copper. You are treating it with H2SO4, you are getting SO2. And you can also take sodium sulfite, again H2SO4. Now also we are getting SO2. So this is a laboratory method, that is small scale method. Any doubt here? Now there are some important structural features of sulfur dioxide, so that is why we are discussing it. Sulfur dioxide, one picture we have already seen. Okay. Now this in the last slide, this type of picture we have seen, that is OS plus minus double bond O. But another resonance structure is also possible, which is like this. So in this case, see, there is one lone pair, that is 6 valence electrons, 2 electrons non-bonding, and the 4 electrons they are making covalent bond. So in this structure you have seen coordinate bond, but here we do not have any coordinate bond. We have 2 sigma bond, 2 pi. So this is another structure possible. These are actually different resonance structures. Okay. Now sulfur, when it is in ground state, that is normal condition, when you are not providing any extra energy, we know the configuration of group 16 NH2 NP4. Now sulfur is from third period, so it will be 3s2 3p4. See, 3s2 3p4. But when it is excited state, now we have provided energy, one of the electron, now it is shifted to 3d. How many unpaired electron you have total? 4. Now there will be hybridization. What hybridization? It is 1s and 2p. Now if hybridization is going on, now after sp2 hybridization, there will be 3 sp2. This is 1 sp2, second sp2, third sp2. In one sp2 there is lone pair of sulfur present. So see, this is the lone pair. Rest of the two sp2, these two sp2 hybrid orbitals form two sulfur oxygen sigma bond. That means here you can see two sigma bond. So these two are used for bond formation with oxygen, but it is sigma bond. And we know when the electrons that are not involved in hybridization, those electrons are actually used for pi bond formation. So these two electrons, one is present in 3p, another one is transferred to 3d. These two electrons will be used for pi bond formation. So these two orbitals overlap to form two additional pi bond with oxygen. So this is one sigma bond, sorry, this side sigma, this is pi. So one pi bond is p pi p pi. That means sulfur is using its 3p, and that is sidewise overlap. It is using 3p and it is using 2p. So this is p pi bond. But the second pi bond, this is the second pi bond, now it is d pi p pi. Because now 3d orbital, this electron is present in 3d orbital. So now it is d and p sidewise overlap. So that is why it is d pi p pi. So why this discussion is important? Because regarding structure, if question is asked that what is the nature of this pi bond? Is it p pi or d pi p pi? Then the answer is one of the pi bond is p pi, another one is d pi. Okay, any doubt? So these are the important features of sulfur dioxide, and we know that when it is sp2, it is having geometry trigonal planar. Okay, so that is coordination number 3. Now one coordination side there is lone pair. This is number 2, this is number 3. And the angle, that is standard angle, that should be present is 120 degree. But here you have not exactly 120 but 119 degree. Now why this slight decrease? It is because of this, to avoid lone pair bond pair repulsion. So that is why the angle will be decreased. Okay, this to avoid this repulsion. Any doubt? So now here we have all the possible structures. These two structures, they are okay, that is equivalent resonance structures. But if we number the oxygen, in the first structure oxygen is double bond having, but here it is negative charge, and number 2 oxygen is now having double bond. But this type of structure is also possible. And if we take the average of these two structures, that is 1 and 2, now we will have this type of structure. Okay, because see here we have that is this bond is not fully formed and not fully broken. So that is why dotted line is used. Sulfur is carrying del plus charge because it is not fully developed charge. If it is fully developed, we write simply plus sign or minus sign. But when it is not fully developed, it is written as plus del or minus del. And some important points. It is angular shaped with an OSO bond, it is bond angle 119.5 degree. Two unique shots of pi bond. One is p pi, another one is d pi. Sulfur is sp2 hybridized and bond order is 1.5. That means here, if you consider this structure only, suppose this is structure number 3. If you are thinking that it is the only structure, then what should be the expected bond order? Expected bond order is 2 because there is double bond between sulfur and oxygen. But actually these other two structures, they also have some contribution. That means it is not fully, you cannot say that it is bond order 2, and also you cannot say that it is bond order 1. That is this single bond I am talking about. So it is not 2, it is not 1, it is something in between. It is 1.5. So bond order is 1.5 because we have to consider all the structures. All the structures has some contribution. The two SO bond lengths, they are equivalent, and it proves that SO2, it is resonance hybrid of two canonical structures, 1 and 2. Okay, so if it is not the case, suppose if this structure is fixed, that is structure 1, then both the bond angle, that is bond length, oxygen sulfur bond length, it should be same. It should be different. That is, two different types of bonds are present. One is OS double bond, another one is single bond. But that you are not getting. You are getting equivalent SO bond length, which proves that you have to consider the average structure. Okay, any doubt? Properties of sulfur dioxide. It is colorless gas, but there is a suffocating odor. Water solubility is very good, 2.2 times heavier than air, liquefies at room temperature under a pressure of 2 atmosphere. So room temperature liquefaction possible, but you have to increase the temperature 2 atmosphere, and boiling point minus 10 degrees centigrade. Chemical properties. Its reaction with water and alkalis. The behavior of SO2, you can find some similarity with CO2. Okay, because CO2 when reacts with water, what we get? We get H2CO3, carbonic acid. Similarly, when SO2 dissolved in water, it forms H2SO3. So you can see these two are analog structure. So as SO2 is non-metallic, so that is why it will have some acidic character. It is sulfurous acid. H2SO4 is sulfuric acid, but this is sulfurous acid. Reaction with alkali sodium hydroxide, it forms Na2SO3 and water. This is also just like carbon dioxide. In case of CO2, you will get Na2CO3, but now it is Na2SO3. And if excess sulfur dioxide present, now there will be further reaction. That is, this Na2H2O3 now further reacts with SO2, and now it is producing NaHSO3. If it is carbon dioxide, the corresponding product will be NaHCO3. Okay, so there is some similarities in their chemical properties. Fine. Some more properties we will discuss in the next class, and also the application of sulfur dioxide. We will end here. So if you have any doubt, please ask. If there is no doubt, we will end the session here. Thank you for listening.